Hello, hi guys. Today we'll be looking at the two-stage velocity diagram. So I'm just responding on the questions that you guys have been asking all along. So I hope this will find you before the examination, which is next week Thursday. So now let's do this question, and then I will do another question. I think I will do three of this question, like examples. So then now we have a two-stage velocity component impulse steam turbine consists of two rows of the moving blade separated by the fixed blade. We know this that this is the moving blade then separated. So as I said on the previous video, this is your velocity diagram. This is two-stage. This is the moving blade, first moving blade separated by this is the fixed blade, and then this is the second moving blade. Okay, now let's continue. Okay, so now if you said the inlet, we have the inlet and the outlet angle of the first row of the moving blade are 25 degrees. So that means we have two velocity. We have the inlet and the outlet. Let me just write here. That means we have the inlet velocity, angle, and then also the outlet, which are equals to 25 degrees Celsius. So this is our inlet angle and the outlet angle. Okay, continuing from there, we have also the outlet angle. Let's say the outlet angle for the fixed blade is this one. So it's 16.5 degrees Celsius. So now when we're talking about the outlet angle of the moving blade, that means we are talking about the velocity or the nozzle velocity on the nozzle angle on the second stage. So this is our fixed blade, and then this is the inlet on the fixed blade, and then this is our outlet on the fixed blade, which is let's write here, which is V is A2, which is equals to 16.5 degrees Celsius. Yeah, okay, and then let's continue again. So now we said we have, okay, now we have the outlet angle. Now the outlet angle of the second row of the moving blade is 30. That means it's our outlet angle. That means it's B. This is on the second it's 30 degrees. Okay, and then now we continue from okay, now we are here. Sorry about the camera there, but it will come out. So then they say that the steam, now the steam discharge at this so the steam discharge exile from the turbine, and then there is a 15 there's a 6% loss of velocity across the across all blades due to friction. That means this one will give us K. So now now they said draw, okay, use the length of 35 millimeter for the moving for the average blade velocity, and and construct the velocity diagram for the turbine in the answer book, and then calculate and then here they say calculate the scale, indicate the length of all the lines as well as the magnitude and of the angles on the diagram. Okay, so now let's go to our angle. So they said we should use our velocity as 35 millimeters. So we don't know the velocity but we do have them they given us this 35. And then we have also they say we have 6% loss. So if they say 6% loss, that means K is equal to 100% minus 6%, so which give us K as 94%. So from 94 we divide by 100, and then that means K will give us 0.994, like that. So this is our coefficient of friction and the velocity diagram. And then they said this one is discharge. They said here the steam is discharge axial from the turbine. That means the outlet velocity at the end or at the second stage, it discharge axial. That means that the angle is 90 degrees. And then we skip this one. We have also their relative velocity. Okay, the relative velocity at the outlet from the first row of the moving plate is 436 meters per second. So this is the relative velocity at the outlet. We know that on the first stage, if we're talking about the outlet, that means we are having V. This is VE on the first the outlet, which is 436 meters per second. Okay, now let us draw the velocity diagram. Now let us draw the 5 millimeters for our initial velocity. We can just draw this 35 millimeters here. So if we do have this 35 millimeters, this is our 35 millimeters, which is a U here. So this is 35 millimeters, and then we are given the inlet and the outlet angle. So the inlet and the outlet angle on both stages. So I will always I will refer to this one so that we can understand that. So here they said the inlet, the first stage, okay, the inlet and the outlet angle for the first stage for the first stage of the moving plate is the 25. So therefore we're going to just measure our 25 here with our compass. So we place our angle here, our compass here. We can start at this side, which is our 25. This is 20, and then this is 25. Just measure our 25 here, and then also on this other side we have, this is 20 and this is 25 here, and measure here. Okay, and then now if you have these lines, just draw straight line like this. We don't have the measurements of this, we don't know the measurement, so we just draw straight line like this, right? Okay, and then now let's go to the second moving plate. So on the second moving plate, let's write it here. Then on the second moving plate, the initial velocity is the same. The initial velocity is the same. So therefore we can just draw like this. Okay, this is our inlet velocity. Okay, so our then they say here on our diagram, they said the outlet angle or for the fixed moving plate, it's a 16.5. So the fixed moving plate, the outlet is this angle here. So we can just measure our angle here, which is 16.5. Place it there and measure 16.5 this side. So this is 5, 10, this is 15, this is 16, and then we have 16.5 here. Okay, and then we can just draw a line here. Still we don't know the magnitude of this line. And then also we have the outlet angle here. So if they said the outlet angle of the second moving of the second row of the moving plate is 30, the outlet, we know that this side here is the outlet, this angle here is our outlet of the moving plate, and then we just measure our 30 this side, this is our 30 and then we draw this our line here. Okay, so now let's start drawing our angle. Now we have exhausted all the information that we are given. So this is all the information that we are given, except for this one. They say the steam is discharged axially from the turbine. So that means if it's discharged axially from the turbine, we don't we just draw straight line here. So if we draw straight line here, that means now we do have the relative velocity of the outlet in stage number 2, and then this one it also we do have on, this is the VE on stage number 2 also. And then we have now the angle. Okay, the angle here was given, which is alpha here was equals to 16.5, and then even this one was given was 30 degrees Celsius. Okay, then now here, which is our initial velocity, we are given as 35 millimeters. So and then remember the coefficient of friction, we say the coefficient of friction is 0.994. So if it's 0.94, let me write here, if our coefficient is 0.94, to get this inlet velocity on the second moving plate, we said VR2 this is V RE2 is equals to K V R I2, which is this is the inlet, which is this side. But now we do have this one, we are looking for this now, so therefore it's equals to VI2 will be equals to VRE 2 all over K. Now we just measure the distance between of these two. So if we're going to measure this distance here, and then and this one we get 40 millimeters, 40, this 1 2 3, that means it's 43 millimeters. So let's write it here, this is 43 millimeters. Now, so if it's 43 millimeters, to get VR2, that means it's 43 millimeters divided by 43 millimeters divided by K, which is 0.94, and then we get our answer there. Okay, let me show. So it's 43 divided by 0.94, and then we get 45.7. so here it's, yeah, they can write it here, they say it's 45.7. so now that we have 45.7, which is VR, this is V I2, which is equals to 45.7 millimeters. Okay, and then now we have to draw the line. We have to measure the 45. Now 45.7, and then we know that this is 45, and then let's just make it 46. If you say this is 46, then make sure that it intercepts this line, because we don't have the angle this side, but we do have this one, and we know that this the inlet is always the inlet velocity is always with the inlet on the nozzle, on the nozzle. Or you can just place it here, and then this is 45, and then 45 here, and then we have 45, therefore this is 46 here, and then they are intercepting here. So if they are intercepting here, and then you can just now draw, you can just draw the straight line Okay, they're intercepting you at this point, so you can just draw this line now. So now your velocity diagram at the second stage is complete now. So you can just measure this one here when it's 82. So we can just say that this vi2 is equals to 82 millimeters, right? So if it's 82 millimeters, and then you can measure the angle this side, and then the angle on this other side, it will be my compass is too big, so that means I have to just draw this line, have to extend this line like this, so that I'll be able to read my angle here. Okay, then if I extended this line, and therefore my angle becomes 25, 6, 7, 8, 9. This is 29, so that means my angle here, it's 29 degrees Celsius, and then this one is 30, and then everything now on the second stage is fine. So then let's go to our first stage now. So we are working this thing backwards now. So on the second stage, now we know that when we were looking for this line here, the velocity that is leaving the nozzle angle, or more leaving the first stage, we know that when it leaves the first stage, it's equals to okay, it's what is it? Okay, it's at v. Okay, we know that here, or to get this one, let me write it here on top. We know that VE it's equals to, come on, okay, it's VI, it's VI2 is equals to E1 multiplied by K. So that means to get this relative velocity, the velocity that is leaving the nozzle, this velocity, it's equals to the coefficient of friction multiplied by this velocity here. But now, because we do have this one velocity, therefore we can just divide it to get VE of the first stage. It will be VI2 all over K, and then this is VI2. We measured that it's 82. Now we got 82 here. We say that this is 82 millimeters. So if it's 82 millimeters, therefore that means here we have 82 divided by our K is 0.494, which is equals to let's say 82 divided by 0.84, it's equals to 87.2. That means this one is 87.2. So now we're going to measure 87 again here, which is 87.2. 87.2 will be here. This is 80, 85, 86, 7. Then it will be somewhere here. From this point to 5, 6, 7. Okay, yeah. This is our line here, and then we have to just draw this line, right? So that means that this is a V on the second stage, which is 87.2 millimeters. And then from this one, now we do have the relative velocity here. So if we do have the relative velocity, we can just measure it here. It gives us 115, 16, 17. So it's VR2 is 117. It's 117 millimeters here. Okay, and then so if we do have this 117 millimeters, that means we can get this one also. So to get that one, we said 117 millimeters divided by our coefficient of friction, which is 0.4, then we get 124. So now we can measure our 124 here. So this is 120, this is 124 is here. Yeah, and then to get that, we can just now draw like this. Okay, now our velocity diagram is complete. So this is VRI1, which is equals to 124.4 millimeters. And then now we can able to measure our nozzle velocity here, which is going to be 158. So it's 158 millimeters. Yeah. Okay, this is VI1. Okay, and then now we are done with our then we can just measure our angles. Now our angle here, it's 21. Yeah, yes, our angle here is 21 degrees Celsius, and then on this side it's on this side is 30, 35, is 37. On this side is 37 degrees Celsius. Okay, so now that we are done with our velocity diagram, remember we draw this without a scale. So now we have to come up with our scale. Remember, when we go to our question here. On our question, they said the relative velocity. Okay, this is the relative velocity of at the outlet. At the outlet from the first moving row, it's 437. So if it's 437, that means this it's 437, 436, sorry, 436 meters per second. So now to come up with our scale, we have to look at this one. So we know that that VR is 110. This VR is 117 millimeters. So if it's 117 millimeters, let me write it here. So if it's 117 millimeters, and it's equals to 436 meters per second. So to get our scale, we can just divide this side with 117 and 117 at this side. So that means now 1 millimeters will be equals to, because this will cancel and get 1 millimeters. So 1 millimeters will be equals to 430. And then we get 3.4. So that means it's 3.72. Okay, let's say 3 meters per second. So that means now 1 millimeter here. This will be our scale. Our scale 1 millimeter is equals to 3.73 meters per second. So then you can be able now to answer the follow-up questions now. So to draw this, you got your 10% now, and then to get the other 10, now you have to answer now the average velocity. The average velocity, which was u, and we were given as 35 millimeters. So now that we do have our scale, which we're going to multiply, is going to be 3.73, and then we get our velocity here, right? And then for nozzle velocity, the nozzle velocity, we know that this is the nozzle velocity, and then we get as 158 millimeters. So if it's 158 millimeters, multiply with our scale, which is 3.73, and then we get our nozzle velocity. And then we continue again to get our velocity of the steam leaving the first stage. So this is the velocity of the steam leaving the first stage, which was 87.2 millimeters. So if it's 87.2 millimeters, we multiply by our scale to get it in meters per second, which is 3.7, and then we get it in meters per second. And then again we go to the velocity of the steam entering the second stage. Velocity of the steam, entering the second stage. So this one that is entering the second stage, we are looking at the inlet velocity. Here, this is one that is entering the second stage. Again, is 45.7. You multiply by your scale and you get your answer. And then you continue to this one, the velocity of the steam. Let me just zoom it. Okay, the velocity of the steam leaving the turbine. The velocity of the steam leaving the turbine. This is the velocity of the steam leaving the turbine here. And we didn't measure it, so we have to measure, get the millimeters first, and then multiply it with our scale. And then the nozzle angle. This is our nozzle angle here. This is our nozzle angle, and the nozzle angle is 21 degrees. And then the energy and the efficiency. This you do have formulas for these two. So I think you find this information useful. So we tune in for the next video. We will just discuss we'll do some few examples, but for these examples I wouldn't be drawing up to scale. We will just do a rough sketch so that we will cover 3 or 4 question in one video. Thank you.